Welcome to the session on the normal distribution, approximating a binomial distribution. The objectives for this session are to approximate a binomial distribution using a normal distribution. In an experiment or survey, when carrying out a number of trials, a random variable x can be defined to represent the number of successful trials. The variable x can be modelled by a binomial distribution b bracket n comma p if the number of trials n is fixed, there are two possible outcomes only, the probability of success p is fixed, and trials are independent of one another. If a random variable x has binomial distribution BNP, then its probability mass function is given by the probability of x equals r equals n choose r p to the power r times 1 minus p to the power n minus r. N is sometimes called the index. P is sometimes referred to as the parameter. C n choose r equals n factorial over r factorial times n minus r factorial, where of course n factorial is n times n minus 1 times all the way down to 3 times 2 times 1, and 0 factorial is equal to 1. This is convention. Also, if the probability of a success equals p, then we can derive the fact that the probability of a failure equals 1 minus p, since of course there are only two possible outcomes. Let's now have a go at an example to illustrate this. Pause the video and have a go. Press play when you're ready to view the solutions. Let's have a go at example 1 part A first. The random variable x is distributed binomially with n equals 9 and p equals 1/3. Find the probability that x equals 3. So let's solve this. We're going to use this highlighted formula. And applying it, we have probability that x equals 3 equals 9 choose 3 times 1/3 to the power 3, where of course 1/3 comes from p equals 1/3, multiplied by 2/3 from 1 minus p to the power 6, which comes from 9 minus 3, or n minus r. So tidying up gives us this expression here. And tidying up some more, we have 84 times 1 over 27 times 64 over 729, which gives us 1,792 divided by 6,561, which is equal to 0.273 to 3 significant figures. It can be challenging to calculate the probabilities for x when n is large with a binomial distribution. Sometimes a normal distribution can be used to approximate a binomial distribution. So let's take a look at this example. Here we have x distributed binomially with number of trials n and the probability of a success p. Notice that this kind of follows the shape of a normal distribution. and we can indeed superimpose upon it a smooth normal distribution curve. And this is represented by the variable y distributed normally with mean mu and variance sigma squared. So theoretically, how do we convert a binomial distribution to a normal distribution? Let's consider the binomial random variable x distributed binomially with number of trials n and probability of success p. Under certain circumstances, this can indeed be approximated to a normal distribution y, distributed normally with mean mu and variance sigma squared. This can be done if n is large and p is close to 0.5. In these circumstances, mu, the mean of the normal distribution, equals n times p, and sigma, the standard deviation of the normal distribution, equals square root of n times p times 1 minus p. So here's a summary of this information here. It is important to note that this approximation is only valid when p is close to 0.5, since the normal distribution is symmetrical. Let's now take a look at an example. If x is distributed binomially with number of trials 60 and probability of a success 0.45, we have that n equals 60 and p equals 0.45. Since p is close to 0.5 and n is large, this can be approximated by the normal distribution. So, mu, the mean of the normal distribution, equals n, which is 60, times p, which is 0.45. And this equals 27. So the value of our mean is 27. And now for the standard deviation. This is equal to square root of np times 1 minus p. So let's plug in the values. N equals 60, p equals 0.45 here, and 1 minus p, or 1 minus 0.45 here, giving us that the standard deviation is equal to 3.85. Let's now take a look at some more examples where we convert a binomial distribution to a normal distribution. The binomial distribution is a discrete distribution. Here, for example, x is distributed binomially with n equal to 20 and p equal to 0.5. The normal distribution is a continuous distribution. Here we've superimposed a normal curve onto the binomial distribution. Here, y is distributed normally with mean mu and variance sigma squared. We can find the mean for the normal distribution by plugging in the value of n and p. So we have n equals 20 times p equals 0.5 to give us 10. So the mean of the normal distribution is 10. Now let's find sigma squared. This is given by the formula np times 1 minus p. So let's plug in the values. N equals 20, p equals 0.5, and 1 minus p equals 1 minus 0.5, which equals 5. So our variance for the normal distribution is equal to 5. Let's now take a look at something else which is related to problems or issues when converting from a discrete to a continuous variable. Since the binomial distribution is discrete, and the normal distribution is continuous, we need to take into account that when using the normal distribution to approximate the binomial distribution, we need to use a continuity correction. So for example, if we want to find the probability that x is greater than 6, then this is going to be approximately equal to probability of y being greater than 6.5. And similarly, if we want to find the value of probability x equal to 14, this is going to be approximately equal to the probability that y is greater than 13.5 and less than 14.5. And this is called the continuity correction, and we need to implement this when we're converting from the binomial to the normal. And similarly, when we're looking at the probability that x is less than or equal to 3, this is approximately equal to the probability that y is less than 3.5. Now let's take a look at an example. Pause the video and have a go. Press play when you're ready to view the solutions. Let's take a look at part A first. A biased coin has the probability of a tail equal to 0.47. The coin is tossed 200 times and the number of tails x is noted. Write down a binomial model for x. So let's solve this. We have that x is distributed binomially with n equals 200 because there are 200 tosses of the coin, and p equal to 0.47 because the probability of a tail, which is the success, equals 0.47. And this is our binomial model for x. Now let's take a look at part B. We are required to explain why x can be approximated by a normal distribution, y. So let's solve this. The variable x can be approximated by a normal distribution y, distributed normally with mean mu and variance sigma squared, because n equals 200 is large and p equals 0.47 is close to 0.5. Now for part C. From part B, we know that x can be approximated by a normal distribution. Find the values of the mean and the standard deviation. So remember that mu, the mean, equals n times p. Therefore, since n equals 200 and p equals 0.47, we have that mu, the mean, equals 94. We also have this formula for the standard deviation. Sigma equals square root np times 1 minus p. So let's plug in the values. We have n equals 200 and p equals 0.47 and 1 minus p equals 1 minus 0.47, giving us that sigma equals 7.06. And therefore, y is distributed normally with mean 94 and variance 7.06 squared. Now for part D. Use the approximation found in part C and the continuity correction to find the probability that x is greater than or equal to 70 and less than 80. So let's solve this. From part C, we have that y is distributed normally with mean 94 and variance 7.06 squared. And so if we're calculating the probability that x is between or greater than or equal to 70 and less than 80, then this is going to be approximately equal to the probability that y is greater than 69.5 and less than 79.5. Of course, the variable x is discrete and the variable y is continuous, and this is why we need to add a continuity correction. And in particular, x being less than 80 in a discrete world means that y is less than 79.5. And x being greater than or equal to 70 in the discrete world means that y is greater than 69.5. And so this is equal to the probability that y is less than 79.5 minus the probability that y is less than 69.5. And we can find the probability that y is less than 79.5 by inputting the mean, the standard deviation, and the upper and lower limits in our calculator. This will give us 0.02. Notice here that the mean is 94, the standard deviation is 7.06, and the upper limit is 79.5. For the purposes of our calculator, the lower limit needs to be 10 standard deviations below the mean, just to be on the safe side. Similarly, we can find probability that y is less than 69.5, and inputting the mean, the standard deviation, and the upper and lower limits in our calculator will give us 0.00026. So for this inequality, the mean is again 94, the standard deviation is 7.06, the upper limit is 69.5, and again for the purposes of our calculator we need to have a lower limit which is about 10 standard deviations or more below the mean. And this equals 0.01974. This brings us to the end of this session. If you have understood its contents, you should be able to approximate a binomial distribution using a normal distribution. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.